Good afternoon, everybody. My name is Edoardo, and welcome to the DIM Technologies webinar. Today, the title is Flow Chemistry in Academic Research, Why Static Mixing Matters. Today's speakers are Dr. Malek Ibrahim, CEO of Redim Technologies, and Dr. Olga Guzernikova, Group Leader at Technical University of Vienna. Today's agenda will begin with Dr. Malek Ibrahim, who will introduce the fundamental concepts of flow chemistry and then discuss the importance of static mixing in this field. Following that, our guest speaker, Dr. Guzernikova, will present a real-world application that ultimately led to a publication with our reactor. We will conclude the session with a Q&A discussion. Thank you all for joining us, and now, Malek, the stage is yours.
Is my screen showing up now?
Yes, Malik.
Perfect. All right. Well, thank you very much, Eduardo. Very nice meeting you. My name is Malik, and I'm so happy today to talk about flow chemistry in academic research with a specific focus on static mixing. Maybe before we start talking about science, I could do a quick introduction of myself. So I have my PhD in chemical engineering from University of Illinois in the US, where I worked with Professor Scott Denmark, mostly organic synthesis, process development. Then I did a postdoc in North Carolina State University with Professor Abul Hassani, also focused on organic chemistry, but in this time in flow. And I also worked for a company called Honeywell UOP, very famous in the petrochemical industry, where, as you probably expect, everything happens in flow. And then I moved to Austria and I worked for a research center pharmaceutical engineering, where Professor Oliver Kappa is involved, and he's also a big name in flow chemistry. And about 3 years ago, I became the CEO and managing director of Redim Technologies, which is a company in Graz, Austria, with a focus on developing flow reactors, flow equipment for academic research as well as for industry. So why am I talking to you about flow chemistry? Through my career, I worked on several projects. You can see some examples here on the right side. And as you can expect, a lot of these projects benefited a lot from being done in flow chemistry. And since we've done a lot of these, when we started Redeem as a team of engineers and scientists, we really realize the benefit of flow, and we want to make scientists aware that flow is very important and you can incorporate it in your research with a reasonable amount of effort, and you can magnify the impact of your research. So, in a nutshell, what Redeem does is it provides for academic people flow reactors that are reconfigurable, which means that you can change one piece of the reactor and you can go from a completely different flow, from one flow to a completely different flow, such as a serpentine unit, photoreactor with static mixers, thin film reactors, Holy Sparger reactors, micromixing, a split flow. I mean, we have over 13 different models, and this is like a Lego for flow chemistry, basically. They are very easy to use and they are scalable. So if you identify conditions that work very well and you need to scale it up, we can also scale them up. And they are very cost efficient for academic as well as for industry. Our flow reactors are validated by multiple partners. As you can see here in the projects that we have, CatPose, Light AI Clean, Biopropene, Sahara, Sol2H2. These are all projects that use our equipment for different applications. As you can see here, there is photochemical hydrogen generation. There's also photochemical waste degradation. There's electrochemical decarboxylation, and then there's PEC done in also. We don't only work with partners, we also do direct sales of equipment. And here on the right side, you can see like an example of some of our customers that have our reactors and catalysts in Europe. And yeah, we're not only limited to Europe, we have customers in the Middle East, Australia, and other parts of the world. Yeah. All right, so today I will probably talk for about, let's say, 20 minutes about the items that we have here in the agenda. We will talk about chemistry in batch versus flow reactors, and which one you should go with. Residence time in a flow reactor, why use a flow reactor, how does the flow look like inside your flow reactor, and how to do static or passive mixing in flow reactors, of course. Now, let's start by comparing batch versus flow. So batch is probably the very standard chemistry that you do in a round bottom flask or any container that you have in the lab. And you basically add your reagents, and then you can control your temperature. You probably have mixing or active stirring. You can also control the pressure in some cases. And then the mixing and condition control are applied for the desired reaction. And then you run your reaction for a certain amount of minutes, hours, and then you do a workup, and then you get your product. Now, flow does not work this way. In flow, you're constantly providing reagents, and these reagents flow through your flow reactor, which can be a tube, a vessel, an autoclave, and you normally use a pump or compressor or some sort of feeding equipment for that. And in this case, the reaction time is the time that the reagents actually spend inside the reactor itself. In batch chemistry, key factors are mixing, temperature, and time, variable parameters across time and space. What this means that for you as a user, as you sit and watch your batch reactor, the concentration of the product will increase and of the starting material will go down with time. Yeah. In flow reactor, that's not the case. You will be collecting product of the same quality, same purity, same conversion with time. What you will be controlling in this case is flow rate. You can easily control temperature and pressure. You can also get steady state operation, which is very good if you want to have reproducible quality of the reaction that you're doing. Yeah. So he basically explains to you how the concentrations look like in a batch and a flow reactor. So in batch, you can watch your concentration of starting materials go down as they react and the concentration of the product increase. And this happens versus time. So you normally talk about reaction time. Let me get my laser pointer. Yeah. And then for the plug flow reactors, for example, you have a continuous flow. And when you are at a steady state, the concentrations don't really change with time that you see as a user. They change with reactor length. Yeah. So the longer the reactor, the longer the time that these reagents get to experience together, and the concentration of your product will increase. And of course, the concentration of the starting material increases as you go through the length of the reactor. Yeah. In this case, you will need to control two things, basically, the flow rate and the volume of your reactor. These are the two things that you need to know if you want to run your reaction on flow. All right, so now we talk about residence time. What is residence time in a flow reactor? It's basically the time that a molecule spends inside the reactor from the entrance to the exit. So if you're driving through a tunnel, it's basically how many seconds or minutes it takes you to go through the entrance, to go from the entrance to the exit of the tunnel. Yeah. And the longer the tunnel, if you go with the same speed, you will spend longer time. And if you're a molecule, this means that there is a higher chance of you doing a reaction. So this is basically how this works. In terms of mathematics, residence time can be calculated from dividing the reactor volume by the flow rate. And the residence time need to be long enough to allow complete conversion. But if you go for a very long residence time, this can actually be a problem. Why is that? To get a very long residence time, you can either have very low flow rates, which means that the mixing is not very good in this case. Mixing is not good. Heat transfer can be a problem, and this may result to poor reaction efficiency. Now, if you go to the other side and decide to have a very long reactor, you can have very high pressure drop. What this means is that you normally need a pump or some sort of a flow delivery to be able to constantly feed your reagent through the reactor. And if there is high pressure drop, this means that you need a pump that's very strong that can supply your reactants and the reactants can flow through this very long tube. Yeah, and this pressure drop can also be calculated from a very famous equation called Darcy equation. Yeah. So the Darcy equation depends, of course, as you see here, on the length of the tube or the reactor, which is the L factor that you can see here. So the longer the reactor, the higher the pressure drop. So ideally, you want long enough residence time. You don't want very low flow rates, and you also don't want very high pressure drops. And this is basically kind of the essence of chemical engineering that goes around designing flow reactors. And we understand that not every chemist fully understands these things. And it's our job really as chemical engineers to kind of facilitate the adoption of flow chemistry for chemists who really understand their chemistry better than anyone else. So why use a flow reactor? I mean, this is a very important question, but it can have and you want I to go to P, which is your desired product. Yeah. And you go from I to P by doing quenching. But because I is an intermediate, it can also undergo some undesired reaction pathway and become B. B is not a desired product. Yeah. And our goal here is to maximize P, the product, but not B, the byproduct. So if you look here at the bottom curve, yeah, you can look at the time of reaction in seconds. And as you go with the reaction time, you can see that the concentration of S, the starting material, goes down. The concentration of the product P goes up. But also you can see that the concentration of B increases, because if you wait too long, you might start to have B, going back to I and then going to P, or P, which is a desired product, goes back to I, and then I goes to B, which is an undesired product. So ideally, you want to stop the reaction time at the right time so that you do not have a lot of undesired byproduct. And if some of these reactions are very fast, yeah. So you can look here at basically the ideal time is 0.5 seconds. I don't think that you can fill a round bottom flask and empty it in 0.5 seconds. That's probably not very reasonable. So that's a very classic example for why you would want to use a flow reactor. In flow reactors, you can control the residence time. You can have residence time as short as milliseconds if you need, yeah. So here you would add the reactants, and then you have these reagents, the reaction start, you can have a quench, and you basically adjust the flow rates and the reactor volume so that the residence time here is the 0.5 second that you want, and then you get the product. And if you go with this example, for example, you can maximize your desired product concentration and selectivity much more than anything you can achieve in batch reactors, yeah. Here is another example of a reaction. This is an oxidative Heck reaction, yeah, that you can get two products. The desired product is product A, but you can also get B as an undesired product. And the ratio of A to B really depend on the mixing of oxygen, yeah, into the reaction medium, because it's an oxidative coupling reaction. And if you constantly supply oxygen, you will have the desired reaction rate always being the highest, and this will give you higher concentration of the desired product. Yeah. So you can see here in this reactor, this is a reactor where like the starting materials, the catalyst, and the oxygen gas are supplied. There's a membrane. It supplies oxygen to the reaction solution, and then there's basically a membrane, as we said, and then you collect the product at the reactor outlet. And in a 12-hour batch reaction, you can look at the ratio here between the desired product and the undesired product. It's about, let's say, 7 to 3, 7.5 to 2.5. But if you do this in flow, you can actually get this number to be much higher, yeah? So you can get up to 82 to 8 ratio of A to B. In a lot of cases, you cannot achieve these like good to excellent selectivities in batch. They are only attainable in flow. Now, a reactor like this is not so easy to fabricate, and this will bring us to a point that I will talk about later, is like how to make these flow reactors accessible to chemists, basically. And I will be addressing some of this closer to the end of the presentation today. Now, another case for why to use flow reactors is the high area to volume ratio. Yeah, so if you have a round bottom flask, it has an area, which is basically the area of the sphere. And this area is what's available for illumination. This is what's available for heating or cooling. but the volume of this flask is also so large. So if you think of reactor geometry in terms of area to volume, you can actually get significantly higher area to volume with flow reactors compared to batch reactors. And here's an example actually from our labs at Redeem, where we did this oxidative coupling of two phenyl benzoic acids using a photocatalyst and air as a terminal oxidant to basically close the cycle here. And we built this very simple system, very cost efficient, but also very powerful, that allows you to test different configurations of flow photoreactors. Yeah. Here, the reactors, they all have glass window to allow for illumination, but if you see in the back of these reactors, the flow channel look different. Yeah. And here you can see there's these static mixing elements or arrows, and you can have the flow going in one direction or the other. And indeed, how the flow reactor look like makes a huge impact on the reaction efficiency. One of the take-home messages of this presentation is that flow chemistry is good. It's definitely worth investigating, but there is no one reactor that fit all application. Really, the choice of how the flow reactor look like has to be dependent on the type of chemistry that you're doing. Yeah. So here you can look at actually the batch chemistry that happens on the right side, and the batch chemistry takes about 6 hours to get the reaction to completion. Flow reactors, all the tested flow reactors did better than batch, which is not surprising. But look at how different the reaction time is with different configuration of flow reactor. And indeed, you look at this orange line, which is basically the serpentine reactor that we're looking at here, with very specific dimensions, yeah, 1 millimeter deep. It gives you the highest reaction rate. You can actually achieve almost complete conversion in 1 hour compared to 6 hours that you would achieve in batch. Why is that? Because flow reactors maximize area to volume ratios. Another very classic example for flow chemistry also is safety. If you work with something explosive or if you work with something toxic in your lab, it is much more safe to actually do your chemistry in flow reactors. Yeah, flow reactor will always have a more controlled volume. You can actually automate everything. You don't have to handle these chemicals by hand. They are delivered by a pump. Your exposure as a chemist to the chemicals is much less, and also the amount of chemicals that you work with are much less, because you can actually create nanoliters or microliters if you want with flow reactors. That's so easy. But in batch, this can be difficult, as you definitely know. So here are two examples where they used phosphogens and they used sodium azide. Both are, one is highly toxic and the other one is also dangerous to work with. And you can see that the chemistry work even better in flow than in batch. But the main driving force for going to flow here is actually the safety concerns. Yeah. Now we kind of getting closer to the core of the presentation, which is mixing. Yeah. As you probably know, as a chemist, mixing is very important when you have one thing reacting with the other. And here, for example, they are making this ionic liquid, yeah, with these two precursors. And here you basically need some heat to get the reaction to happen. But if you go to very high temperature, you actually get undesired products. And the purity of ionic liquids are so important. Yeah. So you can look here, for example, there's a photo of the batch reactor from simulation. The color coding here is basically temperature. Yeah. The red one that you see here, like close to the center of the reactor, where there is no efficient cooling, temperature can increase. And it increased by about 3 degrees C compared to the temperature at the outside of the reactor. And this is enough to actually create about 4% purity. So the batch can always get 96% purity maximum. That's the highest they can get in batch reactor. But if they do it in flow, they don't have this big orange zone because there is very good mixing. Yeah, so there's no temperature runway. And in this case, you can see that the temperature is blue pretty much everywhere, with the exception of some like green, which is kind of intermediate temperature jump. This allows them to get higher than 99% inflow purity of the desired product, which is ionic liquid in this case. So how does the flow look like inside a flow reactor? I mean, of course, it would be flow. I'm sure that you've seen flow going through a tube before, or through flow going through a conduit or a vessel. For us, in terms of engineering, how do we describe that? We describe that in terms of some dimensionless numbers. You don't need to be the expert in that, but it's good to know these kind of things, and it's really good to know what your, like, for example, Reynolds number is. Reynolds number is the dimensionless number that describe how turbulent or laminar your flow is inside the reactor. Yeah. So laminar flow is basically the flow that happens when all the flow particles are going in pretty much straight lines parallel to each other. There is not that much mixing that happens. Yeah. Turbulent flow happens when you have higher velocity or if you have smaller area for the flow to go through. It's also affected by the density of the flow and the viscosity of the flow. Yeah. So the higher the Reynolds number, the more turbulent it gets. And it's not linear. Yeah. So you can only call a flow turbulent if Reynolds number is higher than 2000. If it's lower than that, then it's mostly laminar in this case. And you can see here at some screenshots taken with like a camera through a transparent reactor for how like flow of this top gray mixing and bottom black flow. You can see at Reynolds 100, it's not that much mixing. We can see the two phases completely separated. 300, you can see better mixing. 500 is even much better mixing. Now everywhere is gray, which is basically mixing of these two colors. Yeah. So higher Reynolds is better for mixing. Now, the other thing is Dean number. And Dean number is a number that describes the vortices that happen when the flow is forced to go in a curvature. There's some centrifugal force that start to happen if the flow is forced to go through a wedge or a bend or a turn. And these Dean vortices are also exploited a lot in flow chemistry to enhance mixing. Yeah. And this can also be calculated, and there are guidance on how high the D number can be to give you good mixing. So if we want to do static mixing or passive mixing, there are actually different strategies of doing that. Now, this we can talk about this for hours and hours, but what I wanted to talk about today is to give you a top view of the different available designs so that you're aware of what exists in terms of static mixing. Yeah. So there is mixing by lamination in flow reactor. Yeah. And that lamination works well as very low Reynolds numbers, even less than 1. Yeah, if you remember the last slide, we said we need 2000 to have a turbulent flow, but this is not possible every time. So we need to have these kind of mixing strategies. The most standard and very basic mixing device that you can have in flow chemistry is called the T mixer, which is basically a T or an elbow that you have one flow coming from one direction, the others come from the other direction, and then they mix and they go in a tube like that, or they go to another type of reactor. And the mixing here happens by diffusion. So one molecule from red will diffuse to the blue, and the other way around can also happen. One molecule from the blue will go to the red. Yeah. And the area available for this exchange or diffusion is basically the interface area between the two phases. So if you have basically a T mixer that look like that, you have this phase basically that I am highlighting with the cursor. This is what's available for the mixing to happen. If you think about it, you can actually design T with like multiple alternating inlets. So I have here like, these whites have one phase and the blacks have different phase. And as they go in now, I basically multiplied the number of interface areas that are available for mixing. Instead of just having one interface area between blue and red, here I have much more, like 1, 2, 3, 4. Yeah, this increases the area a lot for the molecules to diffuse from one phase to the other. The other example is this herringbone structure, and this can be staggered or single. It's basically the flows go through these kind of staggered feature that you can look at the bottom graph to basically have a better understanding of this. This is a 3D model of how these look like, and as the is used in specific cases. So it's, as I said earlier, it's not like one design fits all. You really need to know what your chemistry is and what's rate limiting. If you don't, there are also ways to estimate or shortlist the number of designs that work best for your chemistry. Another strategy for inducing the static or passive mixing is actually called embedded barriers. And as you can imagine, you have the flow going through a conduit, and instead of this conduit being an open area, you put these embedded barriers inside. And when the flow sees a barrier, it goes around it. So as the flow go around it, it starts to make bends and change its direction. So this is still laminar flow, but with many bends. And as the flow bend, there's a higher chance of mixing happening. It's better than having the flow just going in parallel. Yeah. If you think about it, of the cars going through the tunnel, I mean, as you merge through the tunnel, there's a higher chance. You merge or you change lanes. Yeah. There's a higher chance of hopefully not accidents. Accidents are bad, but in chemistry, these collisions are what we need. That's basically what induce the reactions to happen. And this is basically the concept of these barriers, basically. They force the molecules to basically change the lanes and maybe bump into another molecule and do the chemistry. Yeah. And again, you can look at some like very simple static barrier or embedded barriers here in a serpentine reactor. And as you can see here, as the Reynolds number changes, you can get better mixing. So at Reynolds 1, it's still this simple static mixing is not to static mixing strategy is not enough. As you can see, we can still see the difference between white and black phases. You go to Reynolds number 9 by increasing the velocity, still the mixing is not the best. When you go to Reynolds 81, then you start to see that the black and white are mixed actually, and we start to get the gray color. Yeah. So what I want to tell you here is that it's not that you just have some sort of a static mixing and you can have like good mixing at very low Reynolds number or very low flows. That's not how this works. Each of these strategies have its limitations also. Our third strategy for static mixing is zigzag, and the fourth one would be twisted channels. And we put them here together in one slide because they're kind of built on the same concept a bit. It's basically forcing the flow to change direction periodically. So you can think of the flow here coming from the left side. There is red, red, blue. And as it mixes, then we have the green phase. So you can see here mixing started to become perfect about, let's say, the first third of the mixing, and the rest is just for the reaction to happen. So by the third of the links of this zigzag channel, you already had perfect mixing. You can even build on this design and basically have these flow channels going over the dividers to basically enhance mixing even further. Yeah. Now, these are very small channels, and you will only need these if your mixing didn't go well in like a zigzag channel that looks basic like the one at the top. The twisted channel is basically what looks like here. You can see one unit. It's basically the flow goes and it's twisted, which means that the flow goes from up to down and from left to right. And then it goes from right to left and from down to up. And this keeps happening. This keeps repeating as the flow goes from the inlet to the outlet. And the zigzag channel, its range of Reynolds number is 1 to 50. And it basically improves the literal mixing. The twisted channel, its Reynolds number range is a bit wider, 1 to 100 plus. And it induces this rotational flow that we talked about before, and does this transverse fluid motion. And this chaotic advection, you will hear people talk about it a lot in static mixing. This is actually what allows the rapid mixing to happen even at low flow rates. The last one of our static mixer strategies is serpentine flow reactors. And as you can expect from the name, serpentine comes with a lot of bends. Yeah, looks like a snake. And what you see here on the left side is basically a 2D serpentine, which means that the bends happen in the same plane. Yeah. But you can also have 3D serpentines. And then the bends happen in the 3D dimension. Yeah. And you can see here the comparison of like experimental as well as simulation of 2D and 3D. And here you can see like we are counting the bends. Here you actually have 1, 2, 3, 4, 5, 6 bends. Yeah. So here after these 6 bends in the 2D serpentine, we can still see distinction between the red and the blue. So the mixing didn't completely happen after 6 turns. But if we look at the 3D serpentine, again, we're looking at 6 bends here. Let's count them. 1, 2. There is 3 under the cursor that we don't see. Then there's 4 under the cursor that we don't see. There's 5, there's 6. This would be also 1, 2, 3, 4, 5, 6. Here, after 6 turns, we got much better mixing because you can see the green phase here is much more pronounced than what we achieve in 2D serpentine. Yeah. So you can see here the Reynolds number for this kind of serpentine structure is between 5 and 30. The three-dimensional curve channel generate Dean vortices. So if you remember, we talked about the Dean number, which is related to when you force a flow to go through a curvature. These centrifugal forces induce the transverse mixing. And again, we have the chaotic advection here that's caused by these periodic curvatures in the 3D domain, basically. Now, the last one is actually very important if you have a catalyst surface and your reaction involves gas bubbles. Yeah. So you can actually have these micro channels or grooves in your surface. Yeah. So these are represented by these blue lines here. And let's say a coated surface. That coated surface can be a coated photoreactor or an electrode for electrochemistry, or it can be also something for thermochemistry, thermocatalytic. Yeah. If you make these grooves parallel to the direction of flow, the bubble gets detached much easier, as you can see in the top case here. Yeah. So here we have a bubble that's attached to the surface. There are grooves in the surface parallel to the direction of flow, which is in the direction of my cursor. And as you can see here with the camera, the bubble moved. Yeah. So the bubble was here, it moved right. But if you make these channels perpendicular to your flow direction, they will not be effective. The gas bubbles will be sticking on the surface, and it's much less likely that they will move. Yeah. Now you might ask me, so here you're talking about how to facilitate gas bubble leaving. Where is the mixing here? Well, the idea here is to maximize the mixing of the liquid with the solid. But the gas is the phase that inhibits this. So we're actually enhancing the mixing of the liquid with the solid by removing the gas quickly. Yeah. And basically, in this example, you have these grooves that created preferred escape lanes when positioned parallel to the flow. And it actually facilitated the immersion of the bubbles so that they become bigger and they leave. And then when the gas gets detached from the surface faster, it means that the surface is more available to basically get wetted with the liquid and do a reaction. Yeah. So this was actually done for electrodes used for water electrolysis. And you can see here they looked at them also in this example. And you can see these are the grooves that we're talking about, the black ones. Yeah. And the idea is to have the flow going parallel to them. Yeah. So it will be in the x direction in this case. And you can look at the graph here at the top. The number of grooves per centimeter square, air per centimeter square, affects the bubble size. So here, as we go from, let's say, 0 grooves to all the way to 30, the bubble size went down from 300 micrometer all the way down to 60. But if you have so many grooves, they start to reverse, and then you actually start to have bigger bubbles again. You can also look at the release in frequency, which means like how long does the bubble stay on the surface. And as you can see, there's a magic number here in terms of number of grooves per centimeter, which is about 13. This is the number where you have the smallest bubble size and you have the highest frequency of gas releasing, which means that in this case, you will have the electrode, in this case, always available or most available for liquid wetting and for the reaction to happen. Interestingly enough, at this magic number, they managed to increase the hydrogen evolution reaction efficiency by 35% compared to not having these grooves. That was basically an overview. Now I would like to actually give the microphone to Olga. I think she has a very nice example to describe to you how this happens. Olga, the floor is yours.
Thank you, Malik, for very interesting talk. It was also useful for me. So I would like to take over and also explain how we used. Second, I will share my screen. Yeah, hope You can see my screen now.
Yes.
Yes, perfect. So good afternoon, everyone. My name is Olga. I'm group leader at TU Wien, and today I would like to share with you results of our project, which we did together with Redeem, Malik, and the amazing reactors. I will start. Yes, with introduction, actually, what do we do and why do we do what we want to do? I'm working in the field of photocatalysis and plasmon catalysis, and its field specifically relative our days because we cannot rely already only on fossil fuels, and we as scientists are looking for the most efficient way how to utilize renewable energy sources for energy generation. And through different renewable energy, solar energy or light is one of the most promising. Despite now it's still TRL level is from 3 to 6, so I cannot say that there are many industrial sites already happened, but it's a very promising source of energy because it's evident, sustainable, operational costs are quite low, and it actually can work at different scale. And one of the most, I would say, famous example is for the electrochemical hydrogen production, which is introduced in Japan, Nagano, where 100 square meter field is actually populated with photoelectrochemical reactor. So also, I guess that most of you don't know what is plasmons and these type of things. So usually I would like to explain it in very primitive way that many people know photocatalysis, homogeneous, heterogeneous, and in case of heterogeneous, usually we use a semiconductor as a catalyst with excitation energy over than 3 electron volt, which usually runs through the charge separation. In a more even energy demanding way to run chemical reaction is photolysis. So when we would like to directly activate molecule, in this case, we need even more energy, around 4 electron volt or even more. And plasmon catalysis, this is alternative to photocatalysis, where we try to develop materials which can run chemical reaction with very low activation energy, less than 2 electron volt. And one of the most primitive way how to show advantage of this, that if we have reactor or any reaction which we run using UV light, we need a lot of energy, and if we can substitute this with the light source in the visible and near-infrared light, we can save at least 3, 4, 5 times in terms of energy and also estimation cost. So also the main motivation to use visible and near-infrared light, that in the end we want to use sunlight, because if we have a look at the spectrum, UV light is only 7% of the whole daylight spectrum, and over than 80% is actually visible light. So our target is to design materials which can convert light to visible light to chemical reaction. So in the very primitive way, I also can explain this field is possibility to reduce activation energy for some reaction compared to activation energy that we got usually using normal thermal activated catalysis. So in my group at TU Wien and also partially at Uni Wien is focusing on the 3 main application area is plasmon catalysis, which I'm talking today, also surface enhanced Raman spectroscopy using machine learning, and also some plastic upcycling. And over years of working, I actually probed many chemical reaction using the energy of plasmon. So usually what we do, we take reaction which we can run using normal heating, high pressure, or known catalyst, and try to substitute it with visible light. So over years, we probed, for example, Suzuki coupling, CO2 cycle addition, or pollutant degradation. But independently on reaction, what we have to understand in our field that once we have catalytic particles, which are usually plasmonic particles such as gold, silver, size less than 100 nanometers, we can generate so-called hot electrons or hot holes, which is also very similar to photocatalysis. And most of people consider that actually the lifetime and all time scale of reaction is determined by the lifetime of these hot carriers, which is usually in femtosecond scale. However, once I started to be interested in the translation of this plasmon catalysis, at least to larger scale or finding new opportunities, I found out very interesting question that most of people say that yes, this type of catalysis is determined by lifetime of hot carriers, but how about the question that actually once the molecule is located near plasmonic particles, then it becomes important also time which this molecule interact with plasmonic nanoparticles, or residence time or contact time, which is very similar to what Malik was explaining about flow. And then for me, it became very important question if the whole field is correct and doing hypothesis that we only care about femtosecond scales. And probably many published chemistry is actually ignoring very important question: how important is the residence time and time when reagent come to the surface of the catalyst. So by having this question in mind, we started this collaboration project with Hidim, trying to understand if flow chemistry is actually changing plasmonic reactions. And by doing this, I actually have in mind hypothesis that we have to integrate both nanoscale plasmonic mechanism, as I mentioned, with femtosecond lifetime, with microscale reactor engineering. To choose a model example for our research, I chose Suzuki cross-coupling, which is actually one of the most commonly used CC coupling reaction. It's not only environmental friendly, it's quite easy to run and could be realized in small scale and larger scale. This type of chemistry is one of the most promising to bring to the next level of upscale or industrialization, because Suzuki coupling could give you biphenyl, this type of molecules, which are building block for many drugs or organic electronics. So to do our research, we started with design of plasmonic catalyst. In this case, it also was kind of challenge for us to prepare plasmonic catalyst in the gram scale, which should be comparable with flow reactor. So we started with porous aluminium oxide, and then by very simple technique using kitchen microwave, we deposited gold nanoparticles with the following reduction of palladium, which is typical catalyst for Suzuki. And our question was to optimize also the palladium shell that it accelerate Suzuki coupling compared to the reaction without light. So by doing some experimental and also theoretical optimization, we found that 2 nanometer shell actually gives the best performance, and increase of the palladium thickness doesn't make sense. So firstly, we run this Suzuki coupling in a batch, and here you can see the kinetic profile of the reaction. And then we tried to do the same reaction in the flow reactor. In order to do this, we used a commercially available LED source with a wavelength which correspond to the maximum of plasmon resonance for our catalyst. Here was a situated reactor, then it was connected to the peristaltic pump. And inside the reactor, we poured our catalyst, plasmonic nanoparticles deposited on aluminum oxide, and initial reagent for Suzuki. And as you can see, in optimized condition, as the best, at the best condition, we could reach much faster quantitative yield. So we could increase the yield up to 100%, but 7 times faster than in batch. And also we could increase turnover number and quantum yield. So this is how it looked. But now I want also to give a few details about why in the end I think it worked for us. So when we started optimization of our chemistry, so this is a type of reactor we used, and we also probed different flow rate and different direction, forward and backward. So firstly, we could see that in case of backward reactions, the particle reside much longer and populated over the whole reactor compared to the forward flow. And we can see that also flow direction actually affects a lot. But the most important parameter which affect our chemistry was the flow rate. So we tested 60, 120, and 240 milliliter per minute. And here you can see the yield of the target product at a fixed time. And as you can see, surprisingly, the best result we got with the low flow rate. And if we increase flow rate, then actually yield drops. And it also was the question for us, why exactly it happens like this? Because kind of intuitively you can think, okay, if we increase flow rate, yes, maybe we can switch from laminar mode, or we can get better mixing. But in this case, the situation was even more interesting. So here you can see the catalytic cycle of Suzuki. This type of intermediates are well known and studied over the last 20 years. And the key intermediate in the Suzuki coupling is when palladium ions is actually embedded inside brombenzene. And also it's well known that the lifetime of this intermediate is about half of second, with a full catalytic cycle of 38 seconds. And what we can see is that actually once the residence time decreased to 0.5, which happened in the accelerated flow rate, then the yield dropped. So our hypothesis was that probably because in case of low flow rate, the residence time is long enough, that actually the key intermediate is forming and proceed to the further catalytic cycle. So here you can have a look into more detail. So this brombenzene should be activated using plasmonic energy to embed palladium. And this stage is known as stage limiting intermediate. So as I said, probably because the residence time is large enough, we have enough moment to form this one. So commonly in our field is considered that the only lifetime of hot carriers is important, and most of people actually ignore the residence time of the catalyst and molecule. So to prove this, we performed some electrochemical measurement. In this case, it was with rotating electrode setup, but actually now, as Redeem has also option with flow reactor and possibility to connect electrodes. Once it also will be very interesting for me to repeat this experiment in real flow. But in this case, the setup was that we deposited particles on the electrode. Then we put we actually could imitate different mass transport inside. So in this electrochemical setup, we were testing the cleavage of C-bromine bond and trying to identify if this cleavage depends on the mass transfer. And as you can see here on the bottom graph, if we increase mass transport coefficient, which is related to the flow rate, we get higher photocurrent response, which is kind of the measure of successful reaction. So by doing this, we proved actually that in the field of photocatalysis and plasmonic chemistry, the residence time and mass transport is playing as equal important role as the lifetime of the hot carriers. So in the end, I calculated the flux parameter for plasmon process, which is in how many molecules are converted per square area of reactor per second. And I also calculated flux for the diffusion of the molecule. And what we found that actually they are comparable, so they are with the same range. So it means that these two processes are actually competing and they are both playing very important role in the catalysis. So as a kind of conclusion, as an academic example, I would like to say that once people could think that transfer your chemistry from batch to the flow could look for some people as a simple upscaling, but actually in my field, in the field of plasmon catalysis, this is not simple upscaling, but also the flow mode brings completely different mechanistic insight and chemistry. So instead of just increasing the scale, we have to design both our catalyst and reactor, also the lifetime of intermediates in our chemistry. Just a few words maybe about future plans that now we continue collaboration with Redeem and we are interested to do some 3D materials which will be compatible with the reactor based on commercial form and also in the future 3D printer, also to see how more advanced plasmonic catalysts can be integrated. So as a conclusion, I would like to say why flow chemistry matters for plasmon catalysis, because there are a few limitations for batch plasmon catalysis, such as poor photometallization, you can have thermal gradient, and the most important is diffusion limited transport. And once we transfer the same process to the flow, we could get following advantages such as control residence time. So as Malik explained that you can design your reactor to set it up. Of course, this type of reactor potentially is more promising for upscaling. They have better transport. And as a result, on my Suzuki coupling, for example, we could get higher apparent quantum yield, turnover number, stability, and in the future, with a few steps, potentially more industrial compatibility. So, and this type of research is actually within the big challenges in my field, in plasmonic chemistry, where the whole field in general is struggling firstly with upscaling and also new reactions. So now we tried non-reaction, but in the future it would be very interesting if we can realize some new type of plasmonic chemistry, which was not possible in bulk setup. So Thank you very much for your attention, and would be also happy to answer your question. And now finish my presentation and would like to give word back to Eduardo.
Yes, thank you. Thank you very much, Olga, for this nice overview about your work. Maybe Malek was looking to having some final word about Redeem.
Sure. Maybe I will not take more than 2 minutes, I promise. Do you see my slides again?
Yes.
All right. So yeah, well, thank you, Olga, very much for the introduction and for that great example. It really shows how like flow can be integrated into the chemistry from the beginning. So to summarize, basically, comparing batch to flow gives you maximum light utilization if you do photochemistry, better heat and mass transfer, better selectivity, and better reproducibility. As I showed you earlier, we at Redeem are specialized in these flow reactors, and we have different models. We would love to actually talk to you and identify the best model or models for your application. Yeah. The reactors that we provide are reconfigurable. So if we do not know how the best reactor should look like, the reactor itself can be reconfigured by you as a user. So they are very user friendly. And you can test different configuration, and this by itself you will learn a lot about the chemistry itself. Yeah, so there is like segmented gas liquid flow with these serpentine reactors. With the static mixers, you can actually have asymmetric mixing if you have the flow going one direction or the other. You can also not just change the shape of the flow channel but also the dimensions with us. Yeah. Maybe the very last thing I want to say is that because some people are like very new to flow, and we want to make sure that this is not overwhelming. So we specialize in flow reactor, but we can also help you with pumps, tubing, fittings, light meters, light sources, and all the accessories that go around it. So if you want like a ready-to-use system, we can also provide that. Yeah. If what you've seen today feels a bit overwhelming, we would love to actually offer you a free consultation hour if you're in academia, and talk about your application and maybe suggest a flow reactor model for you. Also, we will be in the SPIA 13 in Krakowa in June, and then we will be in Zagreb attending the Photo IPAC in July. We will have booth in both events. I mean, we're kind of frequent exhibitor in events in Europe. So if you run into us, we would love to hear from you. And if you want to reach out to us, you can email us at office@Redeem Technologies. You can also scan the barcode and hear our contacts. Yeah. I think that summarizes the presentation for today. I will give it back to you, Eduardo, maybe for the Q&A that we can do also.
Yes, thank you, Malek. So I just want to remind to everybody that for questions, there is on the bottom panel, there are 3 dots where if you click it should show Slido, polling and Q&A, and if you click there, it will open the Q&A section where you can ask questions. I see that we have already some of them. One for Olga to start. Someone was curious to understand in scaling from batch to flow, what was the biggest unexpected challenge that you were facing, if it was catalyst integration, light penetration, pressure drop, or maintaining uniform reactor conditions. So just some of your thoughts, Olga. We cannot hear you.
Eduardo, do we need to unmute something from our side?
Can you hear me now? Yes. Sorry. So thank you for question. I mean, it was a little bit in the beginning challenging. So to understand from which point to start, because you can optimize, yes, kind of. So once you optimize a batch, maybe you think that firstly we thought, okay, that we take the same condition and transfer it to flow and then just vary flow parameters. But when we started to play around, we actually realized that normal optimization of the catalyst amount and everything we have to do again once we started to run the flow chemistry. So maybe the most challenging was to get for us the proper strategy. Should we start the optimization like a normal chemistry or only flow parameters? So I would say this, and a little bit also we had to change. It was unexpected for me that we had to change the protocol how to analyze product, because also our system was with some hydrophobic molecules. This product biphenyl is hydrophobic, and we firstly did reaction in water with a little bit of ethanol, and then the product was a little bit residing in the reactor. So in the beginning I did not think that isolation in the end and product analysis also was a little bit different for me than once you take the probe from flask. I would say these aspects.
Great, thank you. And maybe now a question for Malek. Like someone is asking, when someone wants to start with flow, which reactors are best for someone that is new to the field?
Sure, that's a good question. This is probably the question that we get most. I would say start with a reactor that can be reconfigured. Start with something that can be flexible, something that you can assemble and disassemble, that you can easily clean, and if you have like a particle stuck in there or something that you can easily work with. Yeah, this gives you a lot of control over your flow chemistry. Now, I mean, since I work for Redeem, I would definitely recommend the Redeem product, but as a general recommendation from a scientist, I definitely recommend that you get a reactor that you can reconfigure, that's something that's flexible, that you can disassemble and put together yourself.
Okay, thanks. So maybe one more complicated for you, Malek. So someone is asking if I have a reaction that gives me 5% yield in batch due to product degradation, what should I do? Which kind of parameter should I look, or to which kind of action should I take before testing the reaction in flow, supposing that I have already flow reactors?
Sure. Well, the question, well, first of all, thanks for the question. The question implies that you already know that the reason for the low yield is the product degradation. And it's all about time scale. So if you want to get to a flow reactor, you want to have a feeling for your flow rates, like how much are you willing to pump through the reactor. But what's more important is that you want to have a feeling for the time scale, how many minutes it takes you to get to complete conversion, and in how many minutes or hour does the product degrade. If you have the product itself isolated, I suggest that you take the product, put it in your reaction conditions, and look at the degradation. Let's say after 1 minute, 5 minutes, 10 minutes, 1 hour, and look at how fast this happens. If your reaction gets to completion in a shorter time domain than the time domain for the product degradation, then you will have a very high chance of getting this yield much higher in flow. Yeah. But if your reaction, for example, takes 12 hours, but the product degrade in 2 minutes, then you will need to actually incorporate flow reactor plus other things. And just because of that, the time variation or the time limitation that we have here, we can talk about this offline if you want to reach out to us, because you can incorporate things like an instantaneous reaction separation where you can isolate the product as the form so that they don't undergo the degradation. But that's not just flow, that's flow plus. Yeah.
And now, thank you, Malik. Maybe a question for Olga. So someone is asking how stable were the gold palladium catalyst under the extended flow operation? Did you observe any deactivation mechanism that were less apparent in batch?
Thank you. So in our case, we also deposited this gold palladium on aluminum oxide support, which actually was, I mean, because gold palladium, of course, is very expensive, and just to prepare so many nanoparticles for the flow, it would be very difficult. Therefore, we chose this strategy. So we could regenerate 5 cycles, but yes, after 5 cycles, we also saw some degradation. But honestly, we did not address this more into detail.
Okay, and since you are here, I have another question for you. Why did you choose aluminum oxide as a support? And do you think that changing the aluminum could change also the mass transfer or hot electron transfer significantly?
So actually, our options were just silicon oxide or aluminum oxide, which are typical materials for catalytic support. Honestly, we did not probe other supports because it already worked, and just before we already developed this very simple procedure in kitchen microwave to prepare gold nanoparticles on aluminum support. But as it's kind of I think that if we change supporting material, it could affect the chemistry. I mean, firstly, because how catalysts grow on the surface, and secondly, it's also known that yes, this support potentially can affect the electronic structure or Fermi level of this bimetallic catalyst.
Okay, so seems like a new a new idea for future then. Thank you, Olga. Maybe now a question for Malik again. If I conduct a photoflow reaction, how can I make sure that my entire solution is absorbing the light from the lamp?
Yeah, if you want to do photo flow, you want to maximize your basically light absorption, and you want to make sure that the whole solution is absorbing light. So basically, you want to have an idea. Well, first of all, you need a reactor that can be reconfigured. What I mean by that is that there's a thing in photo flow reactors called illumination depth, and this is basically how deep the photons can go. And you want to have that illumination depth deep enough that you use most of the photons that are incident on the reactor, but not so deep to the point that you have like a black zone in the back of the reactor that no photons go to. And this depends on like the light absorption of your reaction medium. This can be easily measured, but if you do not know it and if you cannot measure it, get a reactor that you can control the illumination depth. So for example, our redeem reactors allows you to control the illumination depths by putting spacers. Yeah, in that assembly, you can have a spacer that allows you to have a deeper illumination depth or a more shallow illumination depth, depending on your reaction medium.
Thanks, Malik. Since you are here, another question that was similar maybe to the first one, but if I want to convert a reaction from batch to flow, and this reaction has never been done in flow, how do I select a reactor to begin with? So kind of a decision tree, I guess.
Yeah, so you really need to answer a few questions, like does the reaction involve multiple phases, gas liquid, gas solid, liquid liquid? Yeah, that's one thing. The other thing is, do I have an idea of what my rate limiting step is? What's limiting the reaction rate? And once you know basically these two things, you will have a better idea answering which reactor you can use. I understand that for new chemistry, you do not always know what the rate limiting step is. And again, that I iterate again, that's why a reactor that can be reconfigured is very useful in this case. Yeah. So get a flow reactor that can be reconfigured. and talk to the experts. Yeah, you'll be surprised. There's experts around that will be willing to talk for free.
Okay, so maybe one last question for you, Malek. Can reactions in flow be done under nitrogen or any other inert gas, I guess?
Easy. That's
How?
actually one of. Yeah, sorry. Go ahead, please.
No, how we can do this?
How we can do this? That's actually one of the reasons why we would want to use flow reactors, because basically, if you want to do that, you can start by purging your flow circuit. So starting from the pump to tube and the flow reactor all the way to the outside, you purge with nitrogen or inert gas, argon or whatever, and then you start pumping your reaction medium. You can actually have your supply vessel also under nitrogen blanket. And then the flow, as it goes through, there is always higher pressure inside the reactor than outside, maybe like a fraction of a psi. So there shouldn't be air going inside. If you are afraid of air going inside the reactor from the outlet, there is a small piece called back pressure regulator, BPR for short. This we can also provide. And this prevents air from going inside your reactor if you don't have flow or if you have very short flow. But as long as you have flow going through the reactor, air should be pushed away from the reactor. So you shouldn't have air leaking in. Yeah. So these are very standard things, and it can be easily implemented, and it has been shown flow reactors that run for days and even weeks without air leaking in. Yeah. Um, Another alternative, which we don't recommend, but it can be done because our reactors are very small, you can actually put them inside glove boxes, and this has been done before. But we think that this is a bit complicated. I mean, if you have the glove box and you have space inside the glove box, you can do that. But we also think that it can be easily done outside of the glove box.
Okay, thanks, Malek. I want to
Thank you.
also Olga again for this very interesting presentation. And with this, I will conclude this webinar. We will upload soon this this webinar on our website. So, and we will send you the link. And of course, if you have any questions, please feel free to contact us at office at redeemtechnologies.com, and we will be happy to answer all your questions. Thank you, and see you. Bye-bye.